Okay, so hi, my name is Serena Ishida. Today, my team and I will be talking about improving forest management, steam hydrogasification of hazardous woody fuel for energy and resource recovery. My team members today that will be talking in this presentation are Rosalie Ayala, Kayla Berna, Sandra Arenas, Robert Lozano, and Marco Ceja. And then our professor is Dr. Zhangju Lu. So right here we have our project in in poster form. So we are going to be talking about each category more into detail in our slides, just so our audience, our viewers can get a better understanding of what's going on in each picture. For our outline, we have Kayla discussing project background. We have Robert talking about our proposed approach, Marco talking about research objectives and methodology, Sandra discussing results, and Rosalie discussing summary.
So for a bit of background, foresty states such as California have a fire-prone natural system during the wildfire season. These states need to manage their natural systems wisely for public safety and environmental benefits. So, for example, according to ca.gov, in 2020, there was a total of a little over 8,000 wildfires just in California, and burning about 1.4 million acres. And this mostly is due to climate change being an issue. A way to manage this is tree trimming and man-made fire breaks, or fire fuel breaks. They are efficient methods to slow or stop the progress of wildfire. Next one, please. All right. And with the management of the forests and everything, it creates woody biomass. And forest biomass is extremely fire hazardous, and it generated from forest activities and everything. Woody biomass is not utilized effectively as a renewable source because it's usually in landfills. Hence, this project as a way of a sustainable solution to improving forest management is demanded.
Okay, so next will be our proposed approach. Okay, steam hydrogasification reaction, or SHR, is a patented high-efficiency and self-sustainable thermochemical technology that can convert carbonaceous materials into renewable energy and fuels. SHR process does not need external hydrogen and water supply except for the startup. So if we look at our diagram, starting with the wet feedstock, which is where we get the leftover biomass from the fires, like all of the wood, it's wet because it's out in nature. We have to pre-treat it, which means we have to dry it out so that we can control the molecular ratios that go into our SHR, our steam hydrogasification reaction. The Department of Energy's National Energy Technology Laboratory has performed an in-depth techno-economic analysis of the SHR process and confirmed that the SHR process has the potential for 12% higher efficiency at an 18% lower capital cost compared to other state-of-the-art gasification technologies. So as you can see from the SHR box, the products that we get from the reaction are hydrogen, methane, carbon dioxide, carbon monoxide, and steam, or water. So after we get those product gases, a process called WGS, or water gas shift reaction, occurs, which is where the carbon monoxide and steam are combined, or they react together to create hydrogen and carbon dioxide, which can be separated, where we can take that hydrogen and recycle it back into the initial process of the SHR, creating a total partial recycle of the hydrogen, where we can keep recycling it over and over again for future processes, and the CO2 can be used for other utilization. The leftover methane-rich synthesis gas can be further upgraded to a synthetic natural gas or other renewable fuels. And a lab-scale gasification system will be used to treat different types of woody biomass.
All right, this next section is research objectives and methodology. So these are the three major research objectives. The first one would be to determine the syngas yield and the char yield. We don't always get the amount of gas and char we put in, so we want to make sure we know how much we are getting back. Then we will see which temperature is the most effective, and determining if the temperature is lower, it might give us a better performance or a lower performance. And then lastly, we'll calculate the conversion efficiency to see at which temperature is the most efficient and which one is would be a better fit for our experiment. And this is the lab scale gasification system. As we can see in the number 1 is the reactor vessel. That's where everything's going to go from the feedstock to the steam to the hydrogen gas. And then we got number 2, which is basically the heating element. In our case, it's coil wrapped in tinfoil. And then number 3 is the gas purge and the release system, which is where the gas is input. The number 4 is our pressure gauge and our temperature gauge. That's going to give us the pressure and the temperature at which the temperature inside of the reactor will be showed to us. Number 5 is the gas collection system. That's where we will insert our Tedler bag and collect the final product gas. And this is an actual representation or the picture of what we're actually working with. As you can see, digital pressure up the top gives us the pressure. To the right is the gas collection system. That's where we connect the Tedler bag to get the final gas, syngas. We have the reactor vessel right below it. That's where number 1, as shown in the left side. The heater, which is the coils, that'll be our heating element, and then our temperature control at the very bottom. We will insert the temperature, and that'll heat up the coils, the heating element.
Next, we have our results. Here we have a picture of our original woody biomass, which was pine wood, and then it was converted into 2 different products. One, which is our resource recovery, which is char, and the other one would be our energy recovery, which is a syngas. Usually syngas is used for other machines and other products, as well as char is used as fertilizer. And then here we have our graph of the different temperatures that we measured our syngas yield. So the bottom is our temperatures and the left is our syngas yield mole per gram of pine wood on a dry basis. So at 650 degrees Celsius, our syngas yield was 6.5 grams. At 750 degrees Celsius was 0.09, and then at 850 was just below 0.09. And for this one is our feedstock conversion efficiency percentage. So for our 3 temperatures at 650, we had it at about 85%. At 750 degrees, we had it at 90. And then at 850 degrees Celsius, we had it about at 95%.
So in this presentation, my teammates covered our project, which was about improving forest management through steam hydrogasification of hazardous woody fuel for energy and resource recovery, which came in the form of syngas and biochar. We talked about the need for sustainable management of hazardous woody fuels in order to prevent forest biomass from ending up in landfills. And we were able to conclude through this project that the process of steam hydrogasification of woody biomass leads to high energy recovery of syngas as well as high feedstock conversion efficiency. So now we have some pictures of us in the lab. On the top left, we have a picture of me, Kayla, and Serena before we start assembling the machine. So we have to weigh the pine wood and weigh the water, which is dependent on the temperature of the test that we're running. Next to it on the top right, we have a picture of me and Robert assembling the machine. So we're tightening the screws on the reactor. On the bottom left, we have a picture of Sandra, Kayla, and Marco during the heating process of the reactor. So depending on the heating process, on the temperature, it'll take longer or shorter. So, and on the bottom right, we have a picture of Serena, Sandra, and Robert also assembling the machine.
So before we conclude our presentation, we have some acknowledgements. First, we would like to thank Dr. Liu for giving us this wonderful opportunity in working in a lab and getting a lot of hands-on experience with valves and the tools in the lab, collecting gas, dealing with high temperatures. In the picture on the left, we have Rosalie. Next, we have Kayla. Third, we have me, Serena. In the middle, we have Dr. Liu. Next, we have Sandra, Robert, and Marco. So I would also like to thank our teammates for arriving in the lab every day, running experiments, and being involved in this project. And then finally, I'd like to thank a few of our sponsors, which is NSME, Chevron for sponsoring this project, the USDA Natural Resource Conservation Service Bakersfield office, San Joaquin Nutrients, and UC Cooperative Extension. So this wraps up our presentation. Thank you, viewers, for your attention.